In this problem, we're supposed to evaluate an integral and see if it's convergent. Now, one of the things that you can do is just kind of forget about your limits for a minute. Let's just do the entire integral like we normally would, and then we'll worry about our actual limits and the fact that one of them is infinity. So let's focus on just doing a basic integral. Forget about your limits. Let's see, one of the things I'd probably do is change this to the power of negative 5/4 instead of having it on the bottom. So x minus 13 to the negative 5/4 power dx. Now when I look at this, I see that there's something inside the parentheses here. So I am going to have to use u substitution. So I'm going to make this be my u. So u equals x minus 13. Then the derivative of u with respect to x will just be 1. And the derivative of u is just 1 dx. So this is my du. So this equals the integral of just u to the negative 5/4 du. And really, sometimes, especially if you're looking at the textbook, they don't even bother doing u substitution when the derivative is just going to be 1. They just kind of cheat and do it in their heads. But technically, this is how you do it. You do a full u substitution. So when we integrate this, this is going to be u, and instead of negative 5/4, we'll add 1. So negative 5/4 plus 1 is negative 1/4. And you divide by your new power of negative 1/4. And normally we would do a plus c, but we don't need to worry about that in this case because we know in the end we are going to have limits. Okay, and then finally, instead of having a u there, let's put our x's back in. We prefer to have our x's in there. So let's do x minus 13 to the negative 1/4. And so dividing by negative 1/4, we can just say this is times negative 4. So this is the integral that we actually get. You could do u, but then you have to change your limits, and sometimes, especially when I'm already worrying about infinities, it's just easier for me to put the x's back in. So in this case, remember, we actually do have limits, so we need to go ahead and do that. So let's say we have this, and we're going to actually evaluate it from x equals 14 to infinity. And it's important here that these were originally x limits, but that's okay because I put my x's back in so I can plug my x numbers into x. Now technically, if you were going to do this, we'd set it up as an actual limit, and we'd say as b goes towards infinity of my negative 4 x minus 13 to the negative 1/4 evaluated from x equals 14 to b. And so we just switch to b instead of infinity. Sometimes I just kind of skip that step and just plug the infinity straight in, but technically you're supposed to actually write a limit when one of your limits here is infinity. Okay, so let's plug everything in. So we'll still have the limit as b goes towards infinity. And let's do the first part first. So we'll have this negative 4. Now this is a negative exponent, so let's rewrite this. So negative 4 times 1 over b minus 13 to the 1/4 power. Minus, and we'll do a negative 4 times 1 over, instead of x, we now have 14. 14 minus 13 to the 1/4 power. Now let's see what we get here. If I was to plug in an infinity here, what's going to happen if I plug in an infinity? So if I put this going towards infinity, then I'm going to have an infinity minus 13, that's an infinity. So I'm going to have really, really big numbers to the 1/4 power. Even though it's the 1/4 power, it's still going to be really, really big numbers. Okay? Because if you have a quadrillion and you do it to the 1/4 power, you're still looking at numbers up in the billions or trillions range. So we still have really big numbers on the bottom, and anytime you have really big numbers on the bottom, this whole term will end up going to 0. Because when you divide by really big numbers, you just get 0. Okay, so down here, 14 minus 13, that should just be 1. To the 1/4 power, that's just the 1. So I think we just get negative 4. Excuse me, positive 4.